How to characterize planetary atmospheres? They could be either very thin, such as the one of Mars shown here, or extremely dense, which is the case of gaseous planets, such as Jupiter or Saturn. Why can some planets retain their atmospheres, while others cannot? In this video, we will explore some answers to these questions. Among the tools we have access to characterize planetary atmospheres is the hydrostatic equilibrium equation. As the name suggests, it expresses an equilibrium between the gas pressure acting in this direction and the gravitational force acting in the opposite direction. We represent these two forces acting on a volume element, and we will see how to use this equation. How to establish the equation of hydrostatic equilibrium, which measures the equilibrium between infinitesimal pressure and an infinitesimal gravitational force. We have drawn here a volume element with an area dA and a height dH. The mass density is md, and this small volume element is at a given altitude, h. H is the altitude in what follows. There is here an infinitesimal pressure, the force of which is dP dA. If we are interested in the pressure exerted on our infinitesimal volume, we can write it as dP dA. Since we seek the equation of hydrostatic equilibrium, this must be equal to minus dF g, which is the gravitational force exerted on this infinitesimal volume. The gravitational force is, of course, the mass of the volume element. That is the density, which depends on the altitude, times the gravitational field, which can also depend on the altitude, times the volume of our small cylinder, dA dH. We see that dA vanishes, and we can then rewrite this equation in this form. dP divided by dH equals minus h dot g h. Depending on the conditions in which we use this equation, we can very often assume that h is a constant. Moreover, if we have a big planet with a relatively thin atmosphere, g is almost independent of the altitude. We can therefore assume gh to be a constant, g. Thus, g, or both of them, can be constants. Let us rewrite the equation of hydrostatic equilibrium that we have just seen. We had dP divided by dH equals negative g. Let us solve this equation. We recall the ideal gas law, which tells us that P equals nKT, with T, the temperature, K, the Boltzmann constant, and N, the numerical density of particles. This numerical density is the mass density over the mean mass of a particle. We have thus here the mean molecular mass. The computation of which we will show later. And mu is the atomic mass unit. Thanks to the ideal gas law, we get an expression for by rearranging the terms, we have that P mu divided by KT, which I plug in the equation of hydrostatic equilibrium to get that dP, not anymore over dH, but over P, minus g mu divided by KT times dH. We have on the left-hand side a dimensionless quantity, so the right-hand side must also be dimensionless. Therefore, the dimension of this term is the inverse of a length. Let us rewrite once again the equation of hydrostatic equilibrium in a slightly different manner. We still have dP divided by P and a term dH we had previously. We had a term which was the inverse of a length here, so we write 1 divided by h, with h equal kT divided by g mu. This equation is now very easy to solve. The pressure is a constant times the exponential of minus h divided by h. H is a characteristic height of the atmosphere. At ground level, when h equals 0, P is the ground pressure. We have thus simply that P is equal to P0 on the ground pressure times the exponential of minus h divided by h. Let us draw this relation on a figure. We can plot either the altitude as a function of the pressure or the other way around. We have here the altitude, h, and here's P. We are thus drawing the pressure profile. The pressure profile is an exponential curve, which looks roughly like this. Here is the zero altitude. So the pressure at this point is P0. At this point, where h equals h, the pressure is P0 divided by E. Again, we are here at ground level and here at high altitude. This, of course, assumes that we have solved this equation in an extremely simple case. A word on the computation of the mean molecular mass, which we noted as a mean. Let us make the computation with the Earth as an example. It represents the mean number of particles in the atmosphere. We simplify the Earth's atmosphere by assuming that there is 78% of molecular nitrogen and 22% of molecular oxygen. What we want to do is to count the mean number of particles in the atmosphere. The molecular nitrogen is N2. The molecular oxygen is O2. The nitrogen atom has 7 protons and 7 neutrons, therefore 14 nucleons. 14 nucleons for one nitrogen atom means that for the molecule N2, we have 28 atomic mass units. The oxygen atom has 16 nucleons. And thus, for O2, we have 32 atomic mass units. What is the mean molecular mass? It is a weighted mean mass. The weights are simply the proportion of each element in the atmosphere. We have 78% times 28 atomic mass unit plus 22% times 32 atomic mass unit, which we normalize to 0.78 plus 0.22, and we find 29 atomic mass unit. Once we have G and H, how can we use this quantity to see, for example, if a planet is able to retain its atmosphere or not? We can consider the escape velocity of a molecule. We can compare the escape velocity of a molecule in the atmosphere with its most probable velocity. If a particle has a very large ejection speed, it can break away from the gravitational attraction of the planet, and as such, the planet does not retain its atmosphere. Therefore, we want to compare the escape velocity of the molecules with the most probable velocity of the molecules in the atmosphere. We write the escape velocity, VE, and it is greater than the mean velocity of the molecules. VE is the escape velocity, which is obtained by computing the kinetic energy of a particle with a mass m and the escape velocity, and equaling this kinetic energy to the potential energy of the particle in the gravitational field G, where r is the planetary radius, since we consider the altitude 0. This relation yields immediately the escape velocity, i.e., the square root of 2g times the radius of the planet. We have on the one hand the escape velocity, and on the other hand, the most probable velocity. We have a gas with thermal agitation. As such, the velocity distribution is a Boltzmann distribution, just like in thermodynamics, and the most probable mean velocity is the Gaussian mean of the velocity distribution, which is equal to the square root of 2kt, where k is still the Boltzmann constant, over mu. Here is where the h we previously saw appears. We can rewrite this mean velocity as the square root of 2gh, where h is the characteristic height we previously computed, the relation we wrote. So VE and the mean Vm can be finally written as a comparison between the planetary radius and the characteristic height of the atmosphere. In such a case, if Rp is greater than h, the planet can keep its atmosphere. We have thus established a very simple relation from the characteristic height of a planet that tells, by simple comparing the planetary radius with the characteristic height of the atmosphere, if a planet can retain its atmosphere or not. Here is the data from the previous video for Venus, the Earth, and Mars, with the addition of the new quantities we just introduced: the pressure at ground level, the characteristic height, h, and the radius of the planets. We first noticed that in the three cases, the planet retains its atmosphere, since h is negligible in regards to the planetary radius. De facto, the three planets, the Earth, Venus, and Mars, have indeed an atmosphere. In the second place, we notice extreme differences between the surface pressures, although the three planets are otherwise very similar, and they moreover have comparable black body temperatures. This shows once again that the composition of the atmospheres and their ability to interact with radiation completely determines the physics at the surface of a planet, as well as the complete temperature and pressure profiles of the atmospheres with the altitude.